Okay, 12.1 and 12.2, part 2. This is part 2. All right, so the math section. Let me see. You don't even know when you see these videos, but I just recorded the other video and I had about 10 minutes. And here's the other one. So I didn't even need that long of a time. I could have probably just gone straight through. Okay, it says at the top of this page, calculate. First of all, it says calculate the average rate at which NO2 gas changes in the first 100 seconds of the experiment. Now, let me talk about how we get reaction rate in an experiment. Rate is the change in the concentration, right? So change means delta. Change in concentration of, we'll just say the reactant. Now, in this case, we'd use the letter A. Think about in algebra, when you first learn algebra, they always said the unknown will be x. The first time you ever saw algebra, probably it said 3 plus x equals 9. You're like, what is x? Oh, okay, 9, so it would be 6. Okay, so x was the unknown. Remember, you always saw x. X is always like the letter. Well, in Kinetics chapter, they like for the unknown to be A. Okay, or the A could stand for anything. A could stand for NO2, A could stand for the chemical NO or O2, depending on what you're working with. So it's like the general symbol they use. Change in concentration. Now, usually we do of the reactants, okay? And some people use R there. I didn't put it in my notes. Change in concentration of R. That might even be better. How about I'll put that too. The change in concentration of the reactants divided by the change in time. You think about it, when you say a car drives at 70 miles per hour, that's a rate, 70 miles every hour. Well, how many molarities change per hour or per minute or per second? That would be, what's the change in molarity over time? Okay, that's what it is. All right, so to get the change in reactant concentration as time goes by, that's usually how we measure the rate. So if I want to make a general term, change in A or change in time, that would be the final molarity minus the initial molarity divided by the final time minus the initial time. So it's a change in Y over change in X. It's the same thing. Y would be your molarity and X would be the time. So you can see it that way. If I put in the initial time, usually it's 0, and what's my final time? My initial molarity and my final molarity. That's the rate right there. Okay, so you could also measure if you wanted to. Oh, and by the way, that number will be negative because the reactants always decrease, so therefore it will always be a negative number. Now, you could also find the change in concentration of products over time, and that would be a positive number. But we'll talk about that. I am going to show you that in some math, but usually we only talk about the reactant. Now, if you know the products change, you can calculate the reactant based on stoichiometry, and I'll show you that in a moment as well. Okay, so the first question, letter A. Calculate the average rate at which NO2 gas changes in the first 100 seconds of the experiment. You're not going to see a whole lot of this in this chapter, but it will happen one time. You'll have to look on the graph that came on the first page, this graph, and you have to probably really blow it up good to see the numbers. Or, you know what, actually even better, you can look at the chart. In fact, I'm really glad this came up. I want to tell you something. When you're in... mostly in graphs, when you're doing graphing, they always tell you if you want to find the slope of a line, find the slope of a line. Don't just take your data points, but look at what your actual graph says. Okay, well in AP, if they give you the data and they give you the graph, you can use the data because it'll be right. It'll work. That's great because they graphed it for you. If they ask you to graph something and find the slope, then you'll do it from your line. But okay, all I'm saying is look at this chart right here. You're allowed to do that. And it says in the first 100 seconds. So at time 0, or number 1, we'll say time 1 was 0 seconds. And then look at time 100 seconds. Well, how about time 1, time 2? Or how about this? final and initial. I use F for final and then a little not symbol. Look at the 0 for the initial. Time initial and time final. And if I want to really be good, like physics, when I write my T, I give it a little curve like that. So that way I don't ever confuse that with a 1 or anything. Okay, 0 seconds. The NO2 molarity was 0.0100. But at 100 seconds, it was 0.0065. Now, that's both molarity. When you see the brackets, that means molar, whether they say it or not. They ought to tell you, though. And it does tell you, yeah, it does tell you at the top above there, real small, right above the NO, concentrations are in mole per liter, mole over liter. Now, okay, so in the first 100 seconds, all we're doing is we're finding out the slope for the first 100. Think of it as like change in concentration. So think of change in, if you don't have to write change in Y or change in X, but that means what is on the, on the graph, on the Y-axis, you had concentration of NO or whatever chemical, NO2, and you had time down here. So, the concentration is your Y and your X is your time. So that's the change in concentration of NO2 divided by the change in time. Now, you don't have to write all this down, but like I'm showing you, if I said calculate this, just say, okay, it's going to be change in NO2 or change in time, which is, you can even just start with this. NO2, the concentration, the molarity final minus NO2 initial divided by the time final minus the time initial. Now, if you really want to be specific on it, time initial was 0, actually. That was time 0. And final time, well, I'll plug it in down here below. Okay, let's just plug it in below. It to be easier. My final molarity was 00.0065 mole per liter. Okay, minus my initial was 0.0100 divided by the final time is, we said 100 seconds, minus the initial time was 0 seconds. Now, you always want to have your units. I'm going to put it over here. All of this is mole per liter, and all of this is seconds. So, when I get the calculation of that, 0065 minus 0.0100, I get a negative number, and that makes sense. It should be negative because this is big. This number is smaller than that one. Negative point. Now it's 0.00. I get 3.5 10 to the negative 3. Maybe I'll just keep it that way. You could put 0.0035 if you wanted to, but I'll write it down that way. 3.5 times 10 to the negative 3 mole per liter divided by 100 seconds. Is it still on the screen? Yeah, it is. Okay, what does that give you? 3.5 divided by 100 is negative 3.5 10 to the negative 5. Now, look at my unit here. This divided by this is negative 3.5 10 to the negative 5 mole per liter per second. Now, what a weird way to write that, mole per liter per second. So what you can do, and what they will do with the units is this. Negative 3.5 10 to the negative 5 mole, then they put liter negative 1 second negative 1. Okay? What a weird thing. Mole, you could, okay, let me go back here first. You could put mole over liter second. You could do it that way too. Or you could put mole liter negative 1 second negative 1. And that's really the official way they like to write this. 3.5 10 to the negative 5. Is it still fitting on the screen? Negative 3.5 10 to the negative 5. It doesn't really fit that good. Mole L negative 1 S negative 1. That is the, let me get around that part. That's the answer. Mole negative 1 S negative 1. That means 3.5 10 to the negative 5 mole per liter per second. Mole per liter is changing every second. All right. Now, I always have 100 things going on at the same time here. And let me see if this is going to work. I want to show you one more thing. Oh, it's not working. Okay, here we go. All right, that's something different I had going on. Two things, three rating circuits going on here. Okay, now, so 3.5, 10 to the negative 5 mole per liter per second. There's something else to do with this. I think, let's see, the next question says, oh no, there isn't anything there. All right. Oh no. No, there is. All right, look at letter B. Oh, wait a minute. Instantaneous rate, don't worry about that one. Average rate, it changes, is the final minus initial. The instantaneous rate, all you do is you take the molarity value at 100 seconds divided by the time, 100. That's all you do. And it's going to be the same thing, actually. Instantaneous rate for that one, won't it? Because it's going to be... No, it won't be. No, it won't be. The instantaneous rate for B, if you want to see example B, if I just did it real quick, it will just be the molarity of NO2 at time 100 divided by the time 100, time 100. So 0.0065 divided by 100 mole per liter per second. So that's going to be what? 6.5, 10 to the negative 1, 2, 3, 4, 5, 10 to the negative 5 mole per liter per second. Okay, I'll just throw that in there real quick. I don't ever see, to be honest, what I just did, A and B, I don't really see them come up much at all. But it could, and this is more important. Later, example D down there at the bottom. We did C already. So example D, this will be the last one. All right, here we give you an equation. Phosphorus trichloride, PCl3, or do I need to... Oh, you know what? That question, I really... let me go back for one moment. It was 3.5, 10 to the negative 5 mole of NO2 per liter per second. Okay, this was the rate we had. If they ask you, what is the rate of O2 at 100 seconds? If they had asked you what will be O2's rate, here's all you would do. This is really important. And this they do ask on the AP. So in the first 100 seconds, that was the rate, technically negative, of NO2. What would be the rate of O2 at 100 seconds? Well, here's what you would do. From moles of NO2, I go to moles of O2. Isn't this easy? Mole to mole. 2 to 1. So it will be just half of that rate. So the moles of NO2 will cancel. Now you have moles of O2. 3.5 10 to the negative 5 divided by 2 is 1.75. Or really it's be 1.8 times 10 to the negative 5 mole per liter per second of oxygen. You're going to put O2 there as well. That would be the rate for the oxygen. That's important, and it was not, I cannot believe I didn't have it in these notes earlier. I was reminded of it when I saw the next problem, what it didn't have. Okay, now the last question just asks you to compare the rates of two chemicals. This is not really going to be too bad. Example D, but let me just show you what they mean by it. D says phosphorus trichloride is prepared, not decomposing, by reacting chlorine, it's on the next page. P4 plus 6 chlorine gives you 4PCl3. All right, so it's kind of what I just did a moment ago, but I'll show you. It says, what is the rate of consumption of Cl2 in the relative to P4? All right, they said on the question, that P4 reacts at 0.025, sorry, 0.025 mole per liter per second. Moles of P per liter per second. I like to write it that way when I'm going to do some stoichiometry with it. All right, that was the initial rate that they talked about here. Now it said, what is the rate of consumption of Cl2 relative to rate of P4 consumption? Okay, so Cl2 should be the same as the phosphorus, but should be, what, 6 times greater. So you can just say, for that question, you could just say it's 6 times greater. You don't have to actually do what I'm going to do here, but it makes sense. Moles of phosphorus, moles of chlorine. Now, phosphorus will be decreasing. It's negative 0.025 mole per liter per second is the initial rate they measured at whatever time. They didn't say what time it was. It doesn't matter. These will all be at the same time. So mole 1 to 6, so 6 times that would get a number. They didn't ask you to calculate it. The question just wants you to say that. It will go 6 times faster than, it will be decreasing 6 times faster than the phosphorus. So if you really want to calculate it, it would be negative 0.15 mole per liter per second for, what was it, for Cl2. Then, question 2 says, that was 1. What is the rate of production of PCl3 relative to P4 consumption? Production of this, how did I not see that? Production of PCl3 relative to that, it will be produced 4 times greater than P4 decreases. And you can see that easy by just taking the number. You know, I won't calculate it out, but if I started here with the moles of the P, well then moles of phosphorus will be here, moles of PCl3 will be here, 4 times the rate. I think it's good to write this down, even though they did not ask for the math. And because this could be a good multiple choice question on an AP. They give it to you and they say, hey, if the initial rate of phosphorus is this, what will be the relative, that's the word we use here, the relative rate of production of PCl3 compared to that? Or what is the rate of PCl3 production compared to P4 consumption? Sometimes they call that production consumption. And it will be formed, produced at 4 times faster the rate that this decreases. Okay, that makes sense, 4 to 1 ratio. But now the weird one is number 3, and that makes you think a little bit more. And it says, what is the rate of production producing PCl3 relative to the rate of Cl2 consumption? So the rate of PCl3 production is, we'll just say 4 compared to the consumption of Cl2. Well, you got, 6 moles of that. So if I were to, I'd have to get the moles of Cl2 consumption first, or I'd have to find the rate first. I mean, if I want to get the actual number, I would. But here, that's the rate. PCl3 produced 4 times as fast as, 4 parts for every 6 part that Cl2 decreases, okay? So what is 4 6 when you divide that out? It's 2/3. So it'll be 2/3 the rate. So that does sound like something they would like to put on an AP question. It could be a multiple choice and you don't even have a calculator. You don't even need a calculator. What would be the rate of PCl3 relative to the, what do you call that? Consumption or disappearance, the rate of Cl2. Let me make it easy. What's the rate of PCl3 relative to the rate of Cl2? It's 4 for every 6 of these, so that means 2/3 the rate. So it will be produced at 2/3 the rate of Cl2. All right. Well, that's the whole thing. So work all that question, all the questions on the worksheet you should be able to do. Most of it is just like quick answers, and I did some of it for you, like with that graph, instantaneous average. That's the same thing I just gave you. And then there's a couple of little math things there. But all right, that's all. I'll see you guys later.